Hi, I'm Sartiko1. I endeavor to give you novel arguments regarding abstruse topics. So today I'd like to talk to you about IR spectroscopy and about how to read those spectra. So before we get started, first, here's a sort of schematic of what types of things absorb in what areas. For example, at 3000 you can see the C to H stretch. At 1700, of course, there's the very strong and famous carbonyl absorption. And what I want to say here is it's really better to have this memorized before you start this video. This video is sort of about recognizing various functional groups for like a test-like situation once you have these basics down. So here we can see a spectrum with various things labeled. When we get started in a moment here, nothing will be labeled. Like for example, here we see the unsaturated C to H bonds at 2980, the carbonyl bond at 1750, and C to O single bond stretches at 1250 and 1050. And we're going to look at another one of these in just a moment. But once we get started, it'll be a situation where we don't have anything labeled. Rather, we'll see the molecule just, again, like a sort of test-like situation, and we'll just be figuring it out as we go on the fly. Okay, so let's go ahead and get started here with our first molecule. Okay, so here's our first molecule. Looking at the top left, we can tell that this must be some sort of totally saturated amine. Moreover, look at about, I guess, 3300 there. There we see a sort of smooth medium peak. Now, because there's just one of them, we know that this has to be a molecule containing only one N to H bond. That means that we know that this is a secondary amine with two C to N bonds and one N to H bond. And we know that has to be true because if it were, say, a primary amine with two N to H bonds, then we'd see two peaks there around 3400 rather than just one, excuse me. Another very important thing to note is that this molecule is totally saturated. Now, we know that from the molecular formula and the double bond equivalencies, but let's say that the molecular formula weren't given to us. We'd still know that it was totally saturated because if you look at 3000, those big jaggedy peaks on the right, every single one of them is to the right of 3000 and none are to the left, and therefore we know there are no unsaturated or sort of C double bond CH structures in this molecule. Okay, so here we see an alcohol. Before we get too far into this, I want to go ahead and suggest that as soon as I flash up a new molecule, like we went from the amine to the alcohol, you guys can go ahead and stop the video and analyze the molecule on your own before actually listening to the way that I go through it. That might be a valuable way to use this video. Okay, anyway, so here we have an alcohol. You can tell that it's an alcohol and not an amine because we have a very broad, strong peak. The transmittance there goes all the way down to like 8% or something, whereas in the amine previously it was a much weaker peak around 3400. We also know that this molecule is once again totally saturated because there are no sort of jaggedy peaks on the left side of 3000, like around 3050 or something. They're all to the right. Okay, so now looking at the molecule and the name here, we can see that we are in fact correct. It is an alcohol. And it is totally unsaturated, and in fact this molecule is 2-pentanol. Okay, let's go ahead and look at our next molecule. Okay, so if you want to go ahead and pause for this molecule, this is a good time. Here we can see that there's a carbonyl absorption at 1700 that's very strong and pretty sharp. That's a dead giveaway that this is a carbonyl. Okay, so my thought process is, I know this is a carbonyl, what kind? Okay, so we see that there's two absorptions at about 2850 and 2750, and that means unequivocally that this molecule must be an aldehyde. Moreover, let's say we didn't know the molecular formula, we would guess that this is probably a pretty simple chemical structure like a C2 molecule because the spectrum is relatively like not busy. And what I mean by not busy is that, you know, there aren't very many peaks compared to some of the other molecules we've already seen, like especially in the 500 to 1500 sort of range there. Okay, so once again, this was acetaldehyde or a C2H4O aldehyde. Okay, next we have this molecule here. This might be the easiest to identify of any molecule whatsoever. This is definitely a carboxylic acid. So my thought process here would be, okay, once again, I look at 1700 and I see a broad, sharp peak, so I immediately think carbonyl. Then I look to my left and I see this huge, monstrous looking peak that extends actually all the way, it looks like from about 3500 all the way down to 2500. That's almost like 1,000 wave numbers wide. The only time you're going to see a huge, monstrous peak like that is in a carboxylic acid. Okay, so let's go ahead and look at the molecular name. Okay, so yeah, looking at the structure of the molecule and the name, we can see it's hexanoic acid. Now, although we might not have known that it's hexanoic acid, we definitely would have known that this was, an unsaturated carboxylic acid, because you can see that the C to H stretches are actually protruding out of the huge carbonyl absorption there. And therefore, and since there are to the left of 3000, we know they must have all been C to H single bonds. Okay, so let's look at a little bit more complex molecule here. Here we see a molecule with a C double bond O stretch at 1720, but if we look at 1600, we see some weak, sharp peaks. That tells me there's C double bond C in this molecule. Moreover, I can confirm that suspicion by looking at the left and right sides of 3000 and seeing that there must be C double bond C and C single bond C carbons, both containing H's or having H's off of them in this molecule, because I do see those jaggedy peaks on the left and right sides of 3000. Moreover, looking at about 1900 and 1800, I see two aromatic resonances. So not only do I know that this molecule has C double bond C, but in fact it's aromatic. Okay, now there's only one more thing to state for this molecule, and that's at looking at about 1150. Also, there are peaks at, it looks like about 1250 and maybe around 1000. Together, those signify that not only is this a carbonyl, as we knew from the peak at 1700, in fact, this is an ester. And we know that because those sort of pretty sharp but not too sharp peaks around 1150 tell me that there's a C single bond O somewhere in this molecule, and in fact, with the together with the carbonyl absorption, I can tell that not simply that this is a carbonyl, but in fact that this molecule is an aromatic ester. Okay, so let's look at our next molecule. Okay, this molecule is actually a little bit tricky. Go ahead and stop the video here and take a stab at it. Okay, so this molecule is actually not an aldehyde, although you could think it would be. So look at, the first thing you do is find the carbonyl stretch at 1700, and you go ahead and assume that this is a carbonyl. Then if you look over to your left, you see that there are two sort of peaks of equal height that look like they could be aldehydic. Now, if those were at 2850, they would be aldehydic, but they're actually closer to 3000. They're around 2950, 2980, something like that. So you can tell that those are not aldehydic H's, rather they're just C single bond H saturated H's. Now, if you look at 1210, you can tell that this is in fact not an aldehyde, it's actually an ester due to that C single bond O stretch. Okay. So here, in fact, is the actual structure of the molecule and the name. And in fact, we can tell that is an ester, although I didn't have time to mention that this is actually an ester that has a C double bond C here, as we can see. And that should have been obvious because there's that little peak there at 1680, it looks like, which is, short and weak but sharp, so it's C double bond C. Okay. Okay, so looking at this molecule, it's immediately sort of interesting because we see two very strong, sharp peaks like we normally would expect for carbonyl, but they're between 1600 and 1700, not between 1700 and 1800. So that's immediately interesting. Also, we see really strong absorptions around like 3400 and 3200, but we know that's not from an amine because those would be weaker, and we know it's not from an alcohol because it's not sort of broad enough. So what is this? Okay, well this is actually going to be an amide. Now, the first thing is the the amide has double bond character between the C double bond O and the C single bond N. It's actually sort of double bond character for the N as well. So actually what we're seeing is one C double bond O stretch and then one C double bond N stretch due to that double bond character, even though it's written as a single bond. And those two things to the left are actually two H's that are off the N, like it would be for an amine. Okay, so looking now at the molecular formula and the name, we can see that we are in fact correct. It's a amine with two H's, and we know it must have had two H's because looking at 34 and 3200, there are two peaks and not one, and therefore there are two N single bond H's. And we can see that the amide group there does absorb kind of like a double carbonyl, but too far to the right, again between 16 and 1700. Okay. Okay, so for our next molecule, I'm going to go ahead and tell you that it's not actually something that you'll probably have to know for your class or for the MCAT or anything like that. Um, Looking at it, what you should be able to tell is it's not an alcohol, even though it does have the two O's in there. And also, looking at 2100, there's that very sharp but medium peak. That's a dead giveaway for an alkyne. Um, okay, and also that peak at 3200 is actually going to be the C triple bond C single bond H bond. So that's the alkynyl H there. All right, now looking at the structure and formula of the molecule, we can see that we do in fact have two oxygens in this molecule, even though it doesn't look like it from carbonyl or alcohol absorptions, because they are in fact C single bond O ether-like bonds that are part of an acetal. And we can in fact confirm that by looking at 1200 and 1100 and seeing those C single bond O stretches there. We also see that there is a terminal alkyne in this molecule. Okay, next molecule. In this molecule, we can see we have several double bond equivalencies because it's C9H16O3. But we don't appear to have any C double bond C. So what are the double bond equivalencies? Well, we appear to have at least two carbonyls. And normally you might say one for the peak that looks like that. But if you look at the very bottom of the peak there, you can see that it does have sort of a little zigzag, denoting that this is in fact two separate carbonyl absorptions. And I'm going to go ahead and guess that one's a ketone and the other's probably an ester. Moreover, we know that all those bonds are going to be unsaturated because everything is to the right of the 3000 mark there. I'm sorry, I meant everything will be saturated, not unsaturated. Okay, and I think it's an ester because looking again around like 1160 or around maybe 10,080, I do seem to see a C single bond O stretch there. So yeah, looking at the molecule, it does in fact appear that we are correct. We do have a ketone and an ester, I mean. Another good thing to note here is, look at about 3400 maybe. That little peak right there, don't let that throw you off and assume there's a nitrogen in the molecule. Anomalies like that do happen from time to time, as long as they're small. So I included this compound actually for just a little bit of practice. Go ahead and take a look at the molecular formula, and go ahead and pause the video here and take a stab at what you think this might be, and I'll look at it in just a second. So looking at the molecule with the molecular structure and the name here now, we see that it's an aromatic ester with a phenol, not just an aromatic, and we can tell that that OH must have been often aromatic because it's actually sharper than it normally would be. Normally an O single bond H will be broader and sort of smoother, but here it's a little bit sharper. Okay, we can also tell it's a carbonyl due to the absorption, of course, at 1700. And we can also tell this is going to be aromatic because we do in fact see several C double bond C absorptions there. So even though there's not much to the left of 3000, it is reasonable to assume that this is an aromatic structure. Okay, so that's it for this molecule. Let's go ahead and look at the next one. Okay, so this is going to be our last molecule of the day. Go ahead and pause here if you want to try to work on your own, but I will warn you it is tricky. Okay, so now talking about the molecule. First of all, we see a bond that's not strong enough to be carbonyl at like 1690, but too far to the left to be an alkene. It should be at 1600. So if it's neither C double bond O nor C double bond C, maybe it's C double bond N. And in fact it is. This is going to be an oxime, and we know it's an oxime for two reasons. First of all, the location and strength of that peak, and second of all, looking over at like 3300, we see a broad, strong peak that tells us alcohol, but it has that weird sort of dip in it that's not normal for an alcohol. So I'm going to go ahead and assume that this molecule contains a C double bond N single bond OH. So let's look at the molecule. Okay, so taking a look at the molecular structure and name now, we see that it is in fact an oxime with what we predicted in it. One thing we didn't note is, once again, there are lots of saturated C single bond H's here. But I think really the thing to take away from this is, don't be fooled. You know what a carbonyl peak is. You know it's strong. You know what an alkene is, and you know that's before 1680. So you should have been able to get this guy. If you didn't, don't worry about it too much. You probably won't see that in undergraduate class. Okay, I'm gonna throw some links down at the bottom of this video. Um, go check those out if you want more practice. I'm Sarahiko1. Thank you very much for watching. Goodbye.